Hello and welcome to this next topic, topic 16 of OCR A Level Chemistry. This one's all about the humble alkenes. Now, the stuff we already know, alkenes are unsaturated because they contain a carbon-carbon double bond. And they also have carbon-carbon single bonds normally, and carbon-hydrogen bonds almost always. Now, in the last topic, I said that single bonds were called sigma bonds, and that's because the electron density was between the two atoms. Carbon-carbon double bonds contain a sigma bond, but also what's called a pi bond. And a pi bond has electron density above and below the atoms that are involved in the bond. I'll draw the kind of picture that you're expected to be able to do. Now, I won't go into how these are formed, but this bit in the middle is the electron density between the two carbon atoms. This is how we normally expect electrons to be, sitting between two atoms, being shared by both of them. And this one is the first of the double bond. The first bond in that double bond is a sigma bond. And the second bond in that double bond is this. It's a shared pair of electrons, but they exist in areas above and below the plane of the carbon-carbon double bond. And that's called a pi bond. It comes from overlapping p orbitals. And I like to think of that as looking like a p orbital. If I look along this carbon-carbon bond, then there's an area of electron density above, an area of electron density below, and that's what a p orbital looks like. And pi is the Greek letter for p. So if you look along a bond, you can tell what type of bonds they are because of the shape of those areas of electron density. And you don't have to do anything more complicated than that diagram. It's literally just an oval for the sigma bond and a couple of ovals above and below for the pi bond. But that comes in very useful because that electron density above and below is easy to access. It's more easy to break a bond or to access this electron density which is floating above a bond than get in between the two atoms and attack a single bond. That's why the single carbon-carbon bond in alkanes doesn't break, but this double bond breaks all the time. And I'll talk about that in this video. Now, in the last video, I talked about butane. This video, I'm going to talk about but2ene. In the last one, I said that carbon-carbon single bonds have free rotation, and that's true. This is the single bond here, and this is rotating around that bond. But this is but2ene, and it's got a double bond between these two carbons in the middle. And so those don't rotate. It's because of this pi bond above and below that if you try and rotate one of the carbons, then you break that bond. And you can't just break bonds unless you've got enough energy to do so. And at normal temperatures, you can't break that bond. So at normal temperatures, you have a restriction of rotation around that bond. And that restricted rotation gives rise to a whole new kind of isomerism called stereoisomerism. Let me explain how that works. Whereas before, I rotated this all the way around and I said it can be drawn in different ways. So if I draw a couple of ways that you can draw butane, these are just two of the ways you could draw butane. They're just 4 carbons in a row. It could be zigzag, it could go zig and then down. That can rotate however you want. So these two are the same thing. But when you have a carbon-carbon double bond, which you can't rotate around, it matters. It matters if it goes up and then up again, or if it goes up and then down. Those are two different chemicals because I can't just rotate around this pi bond to make it look like the other one. It's stuck in that arrangement. And so these two, where it goes up and up or up and down, would be two different types of chemical. And that's what these chemicals look like. This one is where the CH3 groups are on opposite sides of the double bond. One's above and one's below. And then this is where they're both on the same side of the double bond. Both of them are below. Obviously, if I rotate this around, they're both above. That's the same chemical. The way you know if something exists as two different forms like this is if you rotate one of the carbons around, and that makes something that looks different. So in this case, rotating this one around so that this was on the top would look different. So that's what it would look like if I could rotate it, but I can't rotate it. The only way you can get it to look like that is by breaking bonds and making bonds. And that's a chemical reaction. When you do a chemical reaction, you make new things. So these are not the same as each other. So they have to have different names. Now luckily, naming them is quite a lot easier than explaining why they exist. If the two groups are on opposite sides of the double bond, that's called trans. If the two groups are on the same side of the double bond, that's called cis. So this is trans-but2ene, and this is cis-but2ene. I said the word stereoisomers earlier, so I suppose I should give a definition for that. These are stereoisomers. They have the same structural formula, but they have different arrangements in space. And that's the definition for sterile isomers. If I wrote out the structural formula for both of these, it would go CH3, CH, CH, CH3. And this is exactly the same, CH3, CH, CH, CH3. They have no difference in their structural formula, but they do look different, so they have different spatial arrangements. And wouldn't it be great if that was as easy as it was? But most chemicals are more complicated than just trans or cis-but2e. And so we need to talk about how you do it for more complicated chemicals. And to do that, I need to really explain what cis and trans can do and what they can't do. Now, cis and trans naming only works if the group on the left-hand side, as I've drawn it, and the group on the right-hand side are the same. This prefix cis, or this prefix trans, describes the orientation of two of the same group. So a CH3 and a CH3, or an H and an H. Those are the same group, and so you can say cis. Cis means they're on the same side. Those two groups are on the same side. Trans means they're on opposite sides. Those two groups, the groups that are the same, are on opposite sides. And that's nice. It's easy. But it doesn't work unless you've got the same group on the left and on the right. So here's some examples of some chemicals with double bonds. This one here is 2-chloro-but2ene. And this one will be 1-bromo-1-chloro-prop-1ene. And one of these I can use cis-trans notation for. And it's this one, because it's got the same group on the left-hand side as the right-hand side. So there's a CH3 group here, CH3 group here, they're on the same side, and so it is cis. It'll be called cis-2-chloro-but2ene. But if you look at this chemical, I mean, it looks pretty much as complicated as that chemical over there. But there's no group on the left-hand side, which is the same as one of the groups on the right-hand side. So if I was to say cis, it would have absolutely no meaning, because cis means that those groups are on the same side. And what groups am I talking about? There's no way of knowing, so we need a new way, a better way of explaining chemicals which are more complicated than having the same group on both sides of the double bond. And because we're chemists and we're logical, this new way actually works for all chemicals. So instead of cis and trans, which only work for a select handful, which have the same on the left and right, E and Z, which is the name of the new one, works for all alkenes. But it is a little bit more complicated, because you need to first of all work out which things you're going to talk about, which of the four groups, the CH3, the H, the Cl, and the Br, are the ones that you're going to talk about. And so there's some priority rules. They're called the Cahn-Ingold-Prelog Priority rules. And those are what we need to be able to use in order to determine which ones have priority over the other ones. And I'll explain what I mean by that as we go through the rules. The basics of using E and Z would be you have a left-hand side and you have a right-hand side. And what you do is you make one of the groups on the left-hand side have priority over the other. And so that's the one that you talk about when you're naming the compound. And then you do exactly the same on the other side. You give one of these two priority over the other, and then that's the one that you talk about when you're naming. And so what you end up with is one group on the left-hand side which has priority, one group on the right-hand side that has priority. If they're on the same side, that's Z. And if they're on opposite sides, that's E. And that's the basics. But deciding which one has priority isn't always as simple as that. Sometimes it is really simple. Like in this case, very simple. But in some cases, it's much more complicated. I'm not going to go into the full details of it, but I'm going to give you the basics, because that's all you need for this A-level part. The way that you determine priority is based upon mass. But it's not the mass of the group. It's the mass of each of the atoms in turn. Now for this one, this is a simple one. And I'll go through those rules in order to just show you how it works. And then I'll do a more complicated one so you can see the full extent of the rules. So I'll start with the left-hand side, and I'm going to draw in the atoms which are involved because it makes it easier for me to explain. Okay, so what you do is you look at the first atom which is bonded to the carbon in the double bond. So the carbon here, which is involved in the double bond, it's the left carbon, and I'm looking at the two atoms which are bonded to that. And those are hydrogen and carbon. Whichever one of those has a higher mass takes priority. And in this case, carbon is heavier than hydrogen, and so it's this lower group which takes priority. And then I do the same on the right-hand side. I look at the two atoms which are bonded to the carbon on the right-hand side, bromine and chlorine. Whichever one of those has a higher relative atomic mass, that's the one that takes priority. In this case, that's bromine, and so bromine has priority. And so once I've established which one on the left-hand side has priority and which one on the right-hand side has priority, all I do is look at their orientation, and they're on opposite sides of the double bond. So this is E. And the rest of the name is exactly as before. So this would be E, 1 bromo, 1 chloro, prop, 1 ene. And that is how you use the priority rules. We had quite an easy job there, because the first atom that we looked at for both the left-hand side and the right-hand side were different. So we just picked the heavier one. It was easy. But what do you do if the two atoms that you go to are both the same? Well, I'll show you what to do now. Okay, so I've drawn it out almost displayed so you can see all of the atoms that we're going to talk about. This is the double bond. I would suggest if you're going to start trying to name them, then always draw the double bond horizontally. That way you've got a left carbon and a right carbon, and you also have a top and a bottom. I forgot to mention this earlier. All of the bond angles around a carbon-carbon double bond are 120 degrees, and it's trigonal planar. Because there's three directions that the bonds come out of, there's no lone pairs, and so those three bonds get completely as far away from each other as possible, because electron pairs repel, and you get 120 degrees. So, Cahn-Ingold-Prelog Priority rules. We'll start with the left again, and this one, just as simple as the first one. This left carbon is attached to two atoms, this one's a carbon, this one's a chlorine. The chlorine is heavier than the carbon, and so the chlorine has priority. And it's important to note that this bottom group weighs more than chlorine. C3H7 would weigh more than 1 chlorine, but it doesn't go on the weight of the whole group. It goes on the weight of each atom individually. So chlorine weighs more than carbon, so chlorine has priority. And now I'll do the right side, and this is where it gets a little bit more complicated. And so you see that the right-hand carbon of the double bond is bonded to two atoms which are both carbon. So neither one of them is heavier than the other. And so what do? Well, what you do is you look at the next atoms that are bonded to that atom. And in this case, the bottom has 1, 2, 3 hydrogens on it. And this top carbon is bonded to 2 hydrogens and 1 carbon. And what you do is you add up the mass of all of those atoms. So here, 1, 2, 3 hydrogens is 3. And up here, 2 hydrogens and a carbon is 14. Choose whichever one has a higher mass. If they're all the same again, you go to the next atoms and the next atoms until you get a difference. If you don't have a difference by the time you reach the end of the molecule, it hasn't got stereoisomers. Stereoisomers only exist if when you rotate this around, you get something different. If when you rotate it around, you get exactly the same thing back again, it hasn't got stereoisomers, and there's no need to do E or Z or cis or trans. So, as I said, the top one has priority because of the second atom in the chain. Those 3 atoms weigh 14 rather than the 3 at the bottom. So the top group has priority. And so, same as before, you compare their locations. They're both above the double bond, and so you get Z. The rest of the name I'll quickly work out. It's 1, 2, 3, 4, 5, 6, 7 carbons long, so that's hept. The double bond is on the carbon third from the end, so hept 3ene, and it's got a chloro group and a methyl group, so it would be 4 chloro, 3 methyl, hept 3ene, I believe, with a Z at the beginning. Correct me in the comments if I'm wrong. Hopefully that gives you the idea of how you use those priority rules to determine which one has priority. Next up, we've got to talk about reactivity. And remember, reactivity is based upon the functional group. And the functional group in this case is that carbon-carbon double bond. That bond has to be involved in every reaction that an alkene does because it's an alkene. If it wasn't the alkene that was involved in the reaction, that wouldn't be an alkene reaction. Okay, that's what functional group means. It means when alkenes react like alkenes, it's the alkene part that makes them act like alkenes. if you find yourself doing a reaction with an alkene and not changing the double bond, that's wrong. Now earlier I called alkenes unsaturated, and that's because they're not full. They can take an extra couple of atoms. Because there's a double bond here, so they're bonding twice with each other. If you break that double bond, you can put 2 extra atoms on. One goes onto one of the carbons, one atom goes onto the other carbon. And those are all the reactions that we really need to know for alkenes. You break the double bond, and then you put 2 atoms on. Now it depends what you're reacting it with as to what those 2 atoms you put on are, but that's how they all work. Okay, so I'm going to start off with the easiest of the alkenes. This is ethene. I'm just going to add stuff to it. These are addition reactions, because I'm just going to take molecules and just plonk them on. The first one you've done already is hydrogen. At GCSE you study hydrogenation, so adding hydrogen at 60 degrees with a nickel catalyst. This is an alkene, so you can add hydrogen to it. What you do is you just take hydrogen and you just plonk 1 hydrogen on each carbon. So you get ethane. You break the double bond and you put the 2 atoms that are reacting, one on one carbon, one on the other carbon. Other things that you can add are halogens. So if I took bromine and I added bromine liquid to this, then 1 bromine would go onto 1 carbon, the other bromine of the diatomic molecule would go onto the other carbon, the carbon double bond would break, and you'd end up with 1,2-dibromoethane. So all we did, we broke the double bond, and then put 1 atom on 1 carbon, 1 atom on the other carbon, and then just draw it. And this reaction doesn't need any kind of special conditions, whereas this top one needed nickel catalyst to make it work quickly. Adding bromine is actually the test for an alkene. So all you do is you put bromine water in and shake it. It's in GCSE as well. Bromine water and shake with an alkene goes colourless from orangey red. What else can we add then? You could add a hydrogen bromide, for instance. Any hydrogen halide you could react with an alkene. So you get a hydrogen go on one of the carbons and a halide go on the other one. And that's all you need to do. You've got chlorine on one of the carbons, hydrogen on the other carbon, and that's called chloroethane. Other things we can add are water. Now water's slightly more difficult because bromine's got 2 atoms, hydrogen's got 2 atoms, hydrogen chloride's got 2 atoms, water's got 3 atoms. But what you do is you just put H onto one carbon and OH onto the other carbon. And so you get an alcohol, in this case ethanol. Now with this one there are some special conditions. You need to heat it, so the water is going to be steam. And you also need phosphoric acid catalyst. And that is also at GCSE, we call that one the hydration of ethene. It's a way of making ethanol. The other way, of course, is fermentation from sugar and yeast. And so those are all the addition reactions that we need to know about. Adding a halogen, adding a hydrogen halide, adding hydrogen, or adding water. The only other thing that we need to be able to add to an alkene is another alkene. And so that's a polymerization reaction. We've done those at GCSE as well. You can add many alkenes together to make a polyalkene. And if you draw your alkene this way, it's quite easy to draw the polymer. And I'll draw one at the top. If, like I've said before, you draw your carbon-carbon double bond horizontally, it's quite easy to go from literally any alkene to any polymer in exactly the same way. You'll have 4 groups, 2 attached to the left carbon, 2 attached to the right carbon. If you just break the double bond and put these bonds extending through the square brackets, put the 2 groups on the left carbon on the left carbon, put the 2 groups from the right carbon on the right carbon in the same way that they are here, so that H goes at the top left, that H goes at the bottom left, etc. And then write a little N on the bottom right hand corner of the square brackets. That's how you do any polymerization reaction. Now, as long as you can draw this original alkene, you can draw the polymer which is made from it in exactly that way every time. And this is called addition polymerization because you're just adding one alkene to another alkene, to another one, and you just add them all together to get addition polymerization. In fact, all of these reactions are called addition reactions because there's only one product, and that product is a combination of the alkene and whatever this thing is that you're adding. And for a couple of these, it's these 2, we need to be able to draw the mechanism for how that reaction works. So I'll do this one, ethene plus bromine, to show you how the bromine actually adds to the alkene. Okay, so we start off with these reactants, and we're going to end with this product, 1,2-dibromoethane. And how do we get there? And you need to use a lot of the stuff we've talked about already. So bromine-bromine bonds are non-polar because they're both the same element, and so their electronegativities are the same as each other. But if you remember what I said about this carbon-carbon double bond, how it's got a pi bond above and below the plane of that bond, that pi bond is full of electrons. It's got 2 electrons, and those electrons repel any electrons that come near them. So as this bromine molecule comes towards the double bond repels the electrons in the bromine molecule to the top, as I've drawn it. So this side becomes slightly negative, and the bottom side becomes slightly positive. That's inducing a dipole the same way as induced dipole-dipole bonds work. And so this positive side, and it's attracted towards double bond now because it wants a pair of electrons. It wants 2 electrons. We call this thing, which is coming in and attacking the double bond, an electrophile. Now, electro obviously comes from electrons, and phile is attraction. So an electrophile is something which is attracted to electrons. But that's not the definition they give you in the specification. The definition they want is it's an electron pair acceptor. This bromine is going to accept a pair of electrons from this double bond. That double bond is going to break, and it's going to make a new bond with the bromine. And so when we do that, when we break a bond and we show what's happening, we need a curly arrow. And the curly arrow shows the movement of the electrons from the double bond to the bromine atom. Bromine can only make 1 bond, and so when it's going to get this new pair of electrons in, it has to break its old bond, and so the bromine-bromine bond breaks, both the electrons go to the bromine atom at the top, making it a bromide ion. This is heterolytic fission, because both of the electrons go to one of the 2, and so the products are different from each other. Okay, so the products of that reaction would be this carbocation. Cation means it's a positive ion, and a positive ion is like carbon, so it's a carbocation. The reason there's a positive charge on that carbon is because where previously it was sharing a pair of electrons, now it's not sharing a pair of electrons, and so the 1 electron that it put in has gone, and the loss of an electron makes something positive. Conversely, this one at the top, this bromine, has gained 2 electrons. One of those electrons was the bromines to begin with, and so that's just an overall gain of 1 electron. So that's a 1- charge. Hopefully you can see what happens here. This negative charge and this positive charge are attracted to each other. Bromine has an extra electron, so it can donate 2 electrons into a covalent bond between it and the carbon. Remember that curly arrows show the movement of 2 electrons, and they have to start at a lone pair or at a bond. This bromide is obviously not making any bonds. It's about to. So it starts off as a lone pair and goes towards the carbon atom. And that reaction between the bromide and the carbocation gives you this product. Now that would be exactly the same no matter what these other groups are attached to the alkene. You can see that they don't get involved at all. So you can now do this for absolutely every alkene, I promise. Just follow those steps. You put the bromine coming in with a dipole on it to show that repulsion of the electrons towards the top of the molecule. Break the double bond by making a bond with this electrophile, and break the bond between the 2 bromines. That leaves you with a carbocation and a bromide ion, and then make a new bond between the bromide and the carbocation to make your product, which we saw earlier as just putting 2 bromines onto those 2 carbons in the double bond. Now this becomes slightly simpler, but also more difficult when you talk about adding hydrogen halides, because hydrogen halides already have a dipole, and so it's the positive side of that hydrogen halide which is attracted to this chemical. But it becomes more difficult when you look at what the 4 groups around the carbon-carbon double bond are, and so I'll talk about that now. Okay, so I've changed the molecule slightly, so now it's propene instead of ethene, and that's just because I needed a different group on one of these to show you how it reacts. And a lot of it is very similar. So you still have the incoming electrophile with the delta positive facing the electrons in the double bond. You still get a break in the double bond to the hydrogen, and you still get the bond between the 2 atoms in the electrophile breaking to form a negative ion on this time a chloride ion. And that's where all the problems start. I ignored it when we talked about the last one because it didn't matter. But with this one it does matter. Which of these two carbons does that hydrogen attach to? It could attach to the carbon on the left, which will give you this intermediate, where the carbocation is on carbon number 2. Or that hydrogen could attach to carbon number 2, the carbon on the right in this case, which will give you a carbocation on this first carbon. And that's going to make a difference because the chloride, if it bonds to that carbon, will give you 2-chloropropane. And the chloride, if it bonds to this carbon, will give you 1-chloropropane. So there's 2 possible products to this reaction. And they are both made. 1-chloropropane and 2-chloropropane. But you get one of them made more than you get the other one made. And you need to be able to say which one, but you don't necessarily need to be able to give a reason. Now I will tell you the reason, but I'll tell you which one gets made more first, and it's always the one which is more substituted. So if you look at this carbocation, or this haloalkane, this carbon is more substituted than this carbon is. And what I mean by that is this carbon has 2 carbon atoms bonded to it, whereas this carbon only has 1 carbon atom bonded to it. And we call that more substituted. The substitution in this case is the number of carbon atoms bonded to 1 carbon atom. Call this one secondary and this one primary. Secondary obviously comes from 2 carbon atoms, primary from 1 carbon atom. There's also tertiary, 3 carbon atoms, and quaternary, which would be 4 carbon atoms. And there's a rule that's called Markovnikov's rule, which states when you add a hydrogen halide to an alkene, the major product is always the more substituted haloalkane. So the halogen goes onto the more substituted carbon. The reason is because this carbocation is more stable than this carbocation. So the more substituted a carbocation is, this one's secondary, this one's primary, the more stable it is, and so the more likely it is to continue on to make the product. And you don't need to be able to explain why a secondary carbocation is more stable than a primary carbocation, or even explain why, in any great detail, 2-chloropropane is made preferentially over 1-chloropropane. The only reason you need to know is that when you add a hydrogen halide to an alkene, the more substituted haloalkane is the major product. We've just got one more bit to talk about. I should have talked about it when I did polymers earlier, but I missed out. And that is the way that we dispose of polymers, or waste polymers. So, waste polymers. What do we do with polymers? They don't tend to break down, they're not biodegradable, and so there's a few things that we can do with them. Polymers contain long carbon-carbon chains, and so what you can do, crack those carbon chains, same way as cracking works at GCSE, to produce many small alkenes and 1 alkane. And all those small alkenes are very useful. You can use those to make new polymers, or you can use those in all these reactions we've talked about, adding hydrogen halides, adding bromine or chlorine, adding water, and all of those things are useful in industry. And so we call that organic feedstock. Feedstock that you feed into organic reactions, which you can then use to make new products. Other things you can do is just burn them. If you burn polymers or waste polymers, then you can create heat energy that can be turned into electrical energy and power homes or schools or factories. But when you do burn them, if those polymers contain chlorine, like PVC, when you burn them, you create hydrogen chloride gas. And hydrogen chloride gas is a very strong acid gas because when it dissolves in water, it makes hydrochloric acid. So you have to remove that hydrochloric acid or the hydrogen chloride from the waste gases before they go into the atmosphere. And the way that you do that is just by reacting it with a base. So what they'll do is they'll just pass that waste gas through something that contains a base, for instance calcium carbonate or calcium hydroxide. The hydrochloric acid will just react with that, and so that hydrogen chloride doesn't go off into the atmosphere and cause acid rain. And so those are the 2 major things that can be done with waste polymers: burning them to create energy for electrical distribution, or cracking them and then using the products as organic feedstock. Now this is only a problem, of course, because polymers don't degrade on their own, and there are new types of polymers that are being made, for instance polylactic acid, which is biodegradable. So if you put it into a landfill, it'll be eaten up by the bacteria and the other things that do biology, and it won't just sit there for decades or centuries or millennia, not degrading and just taking up space. As well as that, you also have photodegradable polymers. So they're made in such a way that when you shine light on them, they slowly break down. Those also better for the environment, especially because these things are often made from renewable sources like cornstarch. So you can change cornstarch into polylactic acid and then use that polylactic acid as a plastic, and that's good for the environment all round. And that is it for alkenes. It's a deceptively large topic. If you've got all the way to the end, well done. Thanks for watching, and hope you join me in the next one. Goodbye.